Welcome back to part 2 of this chapter 4 in CCNA Cybersecurity Operations with me, Joachim Kärrestad from the University of Skövde. And we will actually continue where we left off. We've just discussed mainly addressing and the role of protocols in network communication. And in this part we will talk about connectivity and address resolution protocol, or ARP. So first of all, I want to mention ICMP, and as you remember from last lecture, IP is a best effort protocol. However, you can use the ICMP protocol to provide some feedback about issues relating to the processing of IP packages. So while I said that IP provides no error checking, we can get some error checking by using ICMP. So some of the more common ICMP messages include ICMP echo, which is ping that you may have heard about. You can also have the ICMP message type destination or service unreachable, that basically tells you that you can't reach the IP address that you tried to reach in a timely manner. And we also have time exceeded, which is sort of similar, a timeout when the package doesn't reach destination in a timely manner. So something that's very important in networking is the ability to troubleshooting, to figure out what is wrong. And one part of this is testing if a computer has a working network connection. To do this, we usually use the ping command, which is used to send an ICMP echo request and expect to get an echo reply in return. So this is basically a ping message where we ping a remote computer to verify connectivity. And we can ping the local interface to verify that TCP/IP stack works. So if a user is experiencing connectivity issues, we can begin with trying to ping a remote computer, by sending in, we type ping to send an ICMP echo request, and if we get an echo reply back, we will get a successful message. If that doesn't work, we can try to ping the local loopback interface, which is usually 127.0.0.1, and if we get a successful message back, we at least verify that a local TCP/IP stack works. Another important testing utility is traceroute, and traceroute is also built on ICMP echo reply packages, but it will try to ping every hop, every router on the way from source to destination, and it will tell you where a package fails. So for instance, if we want to communicate, or if I want to communicate from Skövde to a computer in the US, I can use traceroute to see all the hops that the package will have to take along the path from here to the US. And using traceroute, I can see the path that a package is taking, and I can also see where the package is dropped in case something fails. And this can be a very important insight in troubleshooting. So let's rehearse MAC and IP a little bit. As we learned from last lecture, any device will have two address types. So first you have the physical address, the MAC address that is used for communication on the same network, and then you have the logical address, the IP or IPv6 address that is used for end-to-end addressing. So taking this nice example again of PC0 that wants to communicate with PC1, PC1 or PC0 will send the package, address it with the IP address of PC1, which is 192.168.110, but the destination MAC address will be the next hop address, the address of the closest router, because by examining the IP address here, it can realize that this package is going to another network. Then at every hop here, the MAC address part will actually be rewritten. So when the package reaches router 0, router 0 will rewrite the destination MAC address to the destination MAC address of router 1, and router 1 will rewrite the destination MAC address to the MAC address of PC1. So you can see here at how the package is addressed when it reaches PC1 is that the destination MAC address is actually the MAC address of PC1, and the source MAC address is the MAC address of the last hop, so in this case the MAC address of router 1. So computers rely on the subnet mask to know if a package should be sent to a host on the local network or on a remote network. So data for a remote network is forwarded to the default gateway, and data for a device on the local network is addressed to the appropriate device using the MAC address. But to know the MAC address of the recipient, the computer has to use some technology, and that technology is ARP, or Address Resolution Protocol. So basically, when a computer applies MAC addressing to a frame, it will look up the destination MAC address in something that is called the ARP Table or ARP Cache. The ARP Table is a listing of all known IP to MAC address bindings that this computer knows about. So essentially, the computer wants to send the package to a local or to another machine, and it will try to see if it already knows the IP address because it addresses it to the IP address, and it will start by seeing if it knows the MAC address that belongs to this IP address. Well, if it already knows the address, it will address the package and send it on its way. But if it doesn't know the destination MAC address, it will issue something that is called an ARP request. And an ARP request is a broadcast that is sent to all devices on the local network and includes the destination IP address. So it will basically yell out over the network, "Hey, who is this IP address? What's the MAC address that belongs to this IP address?" And the host that has the destination IP address will reply with its MAC address. So when the destination MAC address is figured out in this fashion, the computer will send the package out along its way and store the MAC IP address binding in its ARP table. So once this IP to MAC address mapping has been learned, it's stored in the ARP table for a while that is determined by a timer. And network devices as well as clients will keep track of devices using these ARP tables. And as we will discover later, common attacks on a network is actually attacks that redirects traffic by messing with ARP tables. So if I, as an attacker, can send out ARP replies, in this stage where someone is asking for the MAC address that belongs to an IP address, what if an attacker can intercept that package and reply with a custom reply? So some of the issues with ARP is first concerning the ARP broadcast. If too many devices are powered on at the same time, none of them will have anything in their ARP tables, and they will have to flood the network with ARP broadcast. This may limit performance or impact performance. This is not a too big issue in modern network, to be honest. A more pressing matter is ARP spoofing or ARP poisoning, which is a technique attackers use to provide malicious ARP replies to ARP requests. And this way, an attacker can control where a device sends traffic and may, for instance, position a rogue default gateway. So instead of clients in the network using the correct default gateway, the clients will use the attacker's computer as default gateway, and all traffic sent from the network will be filtered through the attacker's machine, which is not very good. This was quite a short part, so I'll be back soon with the final part of chapter number 4, and until then, feel free to leave questions in the comments field, and see you next time.